In this video, I will introduce descriptors of nodes and how to use them as an example of usage. So often in the literature, you will hear about node centrality measures. So we will speak about the node centrality. I think that it's important to understand that it just means a measure of how important the nodes are in the network, and not necessarily of being central in terms of being in the center. Okay, so a centrality measure is a measure of how important is the node according to some notion of what is important. There are several usages of these centrality measures. So with node description, they are, of course, they can be used to discover important nodes. So maybe you want to, for instance, in a Bitcoin transaction network, to identify some actors which are particularly important. So you will use these centralities to discover them. You can also, it can be used to rank nodes by importance. So if you're interested in one particular node, you might want to know if this node is, compared to the others, more or less important according to a notion of importance. And finally, if you're interested in classifying the categories of nodes, for instance, you can use some machine learning techniques based on these centralities to discover some particular roles. So for instance, in a Bitcoin transaction network, if you want to discover, for instance, user involved in illegal activities, you could compute several centrality measures for all the nodes, and then learn automatically by a machine learning algorithm what centrality scores are, and you can learn to predict from centrality scores if a node is involved in illegal activities or not. So if it's this is maybe a little bit naive as a way to explain it, but basically that's the idea, and you can use these centralities to learn something else about the nodes. So the first type of centrality that we already introduced is very simply the degree of nodes. Okay, so you remember that degree is simply the number of connections. It can be decomposed in a directed networks in degree and out degree. And this notion of the degree is as a centrality is already enough in many cases to find important nodes. So for instance, if you have a social network of interaction in a TV series or in a book, the main characters will be probably the characters with the most interaction with all the characters of the series or the book. So the highest degree will correspond to the main characters of the show or of the series. If you're studying the network of airports and connection between airports by airlines, again, the largest airports will have the most connection. So the highest degree you have, the more important you are. And probably in Bitcoin transaction network, the nodes, the users with the most exchange with other users are probably among the most important ones. But it can also be a little bit more tricky. For instance, in Facebook, the users with the most friends are typically spammers. So people who just try to be friends with as many people as possible to increase their audience. So they are not important in the network. Also on the internet, on Wikipedia, pages with many connections, outgoing connections, they are typically simple list of references. And so they are not what the people are interested in. They are just list of references, so they have many connections, but it doesn't mean they are interesting pages for people. And the other notion of describing nodes that we have already introduced is the clustering coefficient. So if you remember, it corresponds to the density of the neighborhoods, and it tells you if your neighbors know each other or not. Right, so it's this notion of closing triangles around you. So I already introduced it. So now I will introduce some new centralities, and the first one is the farness and closeness. So this one is really a notion of being in the center of a graph. Okay, it's the one which really corresponds to this notion. You can understand it as follows. So if you see the picture of the circle, we know that in a circle, the center of the circle is the node which is the closer in average to all the rest of the circle. If I take a point here, it's very far from this part of the circle. So in average, the center is the closer to the rest of the graph of the circle. And so in a graph, we want to find some equivalent of this center. So you see that the shape of this graph here is kind of a square, and the highest value in red of closeness are kind of in the center. So it's really this notion of being in the center of a graph. So to explain the closeness, it's best to start with the farness, because the farness is simply defined as the average distance to all other nodes in the graph. Okay, so you remember that the distance, we have defined the distance between two nodes as the number of hops on the shortest path. And so the farness is this average distance to all the other nodes. So if you're in the center, you will have a low value of farness. But usually we want a high value for nodes which are important. So we instead take the closeness, so the closeness which is just the inverse of the farness. Okay. So you have here the equation to compute it, and it's best understood on an example. So you see that you have on the top of the fraction n minus 1, so n is the number of nodes. Here there are 12 nodes, so it's 12 minus 1. And on the bottom, you have the average, the sum of the distance to all the other nodes. So for node I, we are computing here for this node, node I, and you see that it has 3 nodes at distance 1, so 3 times 1. Plus it has 7 nodes at distance 2. Okay, so these two nodes are at distance 2, and all these nodes, they are also at distance 2. 1, 2, 1, 2, and so on and so forth. And then you have one node at distance 3. This one, 1, 2, 3. So we see that the closeness of this node is computed like that. So you have this 11 divided by 20. And we see that if we want to compute the closeness of this node, the value will be much higher here. So the closeness will be lower, because this node has only 2 nodes at distance 1, then only 2 nodes at distance 2, then a node at distance 3, another at distance 4, and then all these nodes, they are at distance 5. So it will be a large value here, so a lowest value of closeness. Here you have an example on a real network corresponding to the road network of the city of Amsterdam. And as I explained, you see that the large values in red of closeness correspond to road segments that are in really the center of the city, and the low value are in the periphery. So it's really a way to compute which nodes are central in the network, in the center of the network. The harmonic centrality is a variant of the closeness. It has the same interpretation, and often the values are very similar, but it's just using a harmonic mean to avoid the problem of having disconnected parts. So the closeness centrality, you cannot compute it if the network is disconnected in several parts which are not connected, because then you have infinite values of distance between nodes. So the harmonic centrality is just a way to solve this problem. I don't go into the details. We can discuss about them if you're interested. So the next centrality is also a very important one, and it's a betweenness centrality. So it's a measure of how much the node plays the role of a bridge in the network. So it's very important if you want to understand flows in the network. So for instance, the flow of money in a Bitcoin network. So you want maybe to identify some actors that are important intermediaries. So they are kind of, if you remove them, it will be much harder for the money to flow in the network. So it's defined as the fraction of all the shortest path between all the pairs of nodes going through node U. The betweenness of U is this fraction of all the shortest paths between all pairs of nodes going through U. So the easiest is to do it with an example. So you have again this network, and you want to compute the betweenness of node U. So intuitively, it will be high, it will be a high value, because you see that if you want to go from this part of the graph to this part of the graph, you have to go through this node. So it will be a high betweenness node. So how to compute it? So on the bottom here you have the total numbers of pairs of nodes in the graph, so of other pairs of nodes. So we want to know how many shortest path there is in total in the graph. So there is so it's 11 times 10 because there are 11 green nodes, 11 other nodes, and each of them can be connected to all the other ones, has the shortest path to all the other ones. So this is the total number of paths in the graph, of shortest paths, well, of pairs of nodes in the graph. And on the top, we are computing how many of the shortest paths between nodes are going through U. So, for instance, we know that for these 5 nodes, if they want to go to any of these 6 nodes, they have to go through U. So this means that there are 5 times 6 shortest path between nodes that go through U. Okay, so from this node to this node, I have to do the shortest path is this one, so it's go through U. Between this node and this node, again, I have to go through U. From this node to this node, I have to go through U, and so on and so forth. So, so there are 5 times 6, so 30 pairs of nodes for which the shortest path is going through U. Then there is also this one. If I want to go from this node to this one, I have to go through U again, so it's 1. And then finally, if I want to go from this node to this one, there are 2 possibilities, this one and this one. And one of them, so these are the 2 shortest paths, and one of them is going through U, so I will count it as 1/2. Same thing from this node to this node, right? There are 2 possible shortest paths. So again, 1/2. And I get nothing from all the other pairs of nodes, because if I want to go from this node to this node, I do not go through U. If I go from this node to this node, the shortest path is here, not here. So I'm not going, I'm not passing by U. Again, if I want to go from this node to this node, I don't have to go through U. So this is the total numbers of pairs of nodes, and this is the number of pairs of nodes for which the shortest path between them is going by U. So the problem of this centrality score is that it's quite difficult to compute. It takes a lot of time. So there are some good algorithms actually that allows to do it, and in libraries that you will use, you can use this approximation to get these values. So if I take the same graph as before, on the right, you see that in red you have the high values, and you see that the betweenness this time is not in the center. The nodes with the highest betweenness, they are not in the center. They are in some particular roads, and in particular in Amsterdam, you can understand easily that the bridge that go above the canals, they are important nodes. If you remove a bridge, typically you will make the flow in the network harder. It will be harder to move in this network from one point to another. So these high betweenness nodes, they correspond, or edges, they correspond to nodes that if you remove them, it will be much harder to move in the network. Here is an example for the edge betweenness, which is computed in the same way. This is the railway network of Europe, And so I might ask you the question, what do you think is the highest betweenness edge in this network? So usually the first proposition are some connection like these ones or these ones, which are very central. But actually the highest betweenness in this case will be this connection. So very special connection between all of England and the rest of Europe. And if you remove them, you completely disconnect a large part of the graph. So this edge will have a very high betweenness in this case. Then we move to a different set of centralities which are based on recursive definitions. So this is also something very important that you're actually using every day, even if you don't know it. So the idea of people who introduced this definition was to design a recursive notion of importance. It means that I'm important if I'm connected to important nodes. And so the other nodes, how do I know that they are important? Well, because they also are connected to important nodes. So you see it's a recursive definition, which is a little bit hard to grasp, but so there are several notions, several centralities based on this idea. So the idea of this score is defined such as each node has a score of centrality, and if every node sends its score to its neighbors, so you share your importance to your neighbors, then the sum of all scores received by each node will be equal to its original score. So the sum or the average will be equal to its original score. Okay, so if I have many neighbors which are important, they send me a high score, and so my score will be even more important because it will be the average of many important scores, the sum of many important scores. Okay, so it's defined like this. And this method can actually be solved easily with a method called the power method. So it's very simple to understand. We just put in the beginning a random value on every node. And then we apply what I just described. So every node sends its score to the neighbors. The neighbors, they do the sum or average. And they send to their they compute their new score, then they send this new score to the neighbors, and so on and so forth, until you reach some stable point in which, if you continue to do the process, you keep the same values. And it can be proved that this converge by the Perron-Frobenius theorem, so I don't go in the details in this class, but basically it can be formalized for those who have done some math background. You can formalize it with as an eigenvector problem, and then you can prove that actually finding this solution is equivalent to finding the leading eigenvector of the adjacency matrix. So I don't go into the details, but basically it can be proven that it works. So this is what I just described is called the Eigenvector Centrality. So it's popular and has been used, but it has a problem in the case of directed networks. Because if you remember what I just described, you see that in this directed network, you will have a problem with node A. Because node A will send its score to all the neighbors, but you see that it has no incoming edges. So since it has no incoming edges, then its value will be 0 after the first step, because it receives nothing from the neighbors. So its centrality will be 0. Okay, so why not? But the problem is that in the next step, it will send also 0 to all the neighbors. And you see that for B, B had only one incoming edge, and this incoming edge is from A. So in the second step, it will receive only a 0, so its value will again be a 0. And then if I continue, I see that this node had two incoming edges, but one is A, which is 0, and the other is B, which is also 0 now. So again, this node will have a 0. And actually, you can prove that if your network does not have some particular property, all your nodes will end up with values of 0. So, so this is a problem because these many networks are directed. So, for instance, if you look at transactions, well, transactions are directed. So you probably want something that works on directed networks. And so that's how this algorithm was proposed, which is called PageRank. So maybe some of you already heard about this. And so it was published in a paper by two authors called Sakabrin and Lawrence Page, and maybe you know these names. So if you don't know them, they are the people who created Google. Okay, and so actually this paper that was published, so in 1998, is actually introducing Google. So this paper is really this introduction. So just a side note. So actually, Google is really at the beginning the Google search engine. So when you're going to Google and you're searching for something, the innovation that made it so popular and made Google the company which is today is that it was based on PageRank. It was using PageRank. So just a side note. The paper is quite interesting to read, and in particular, you find this in this original paper. So they say that up until now, most search engine development has gone on at companies with little publication of technical details. This causes search engine technology to remain largely a black art and to be advertising oriented. With Google, we have the strong goal to push more development and understanding into the academic realm. So at that time, they were PhD students, so they were really believing in some big change in the field, but later they changed their mind and they created a company, and then you know the rest of the story. So PageRank is actually very simple. It's just a small modification of what I introduced before. There are two main improvements. One is that they add a constant centrality gain for every node. So if you remember before, if you were a source node, if you had no incoming edge, then after the first step, your value is 0. So what they just do is that they add a very small value to all the nodes at every time. So it solves this problem. And they added another thing, which is that the node with very high centralities, they were giving very high centrality to all of their neighbors. Okay, so if you're very important, you're sending your very important score to all your neighbors, and this kind of make everyone more important every time. And so what they changed is that now what each node is worth is divided equally among its neighbors. So it means that two nodes with the same score of importance, if one has only one neighbor, it will give all its importance to these neighbors. But if, on the contrary, you're kind of a list of all the nodes that exist in the graph, then you will divide your importance to all the other nodes, and so you will not give them some bias. So one node will not be biased just because it's connected to this very important node. Okay, so this is a small modification. I don't go into the details here, but again, it's can be computed as finding the eigenvectors of what is called the Google matrix. But I don't. So again, I don't go into the details. So you might wonder then, what is the link between PageRank and Google search engine? Well, when you do a search on Google, what they do is that they compute the graph of all the pages that contain what the words you have searched for. Okay, so they filter out all the web pages that do not contain the word that you're interested in, and then on this graph they compute the PageRank. So each web page has now one value of centrality of PageRank, and they give you as first result the highest value of PageRank, and second in the list is the page with the second highest value of PageRank, and so on and so forth. So obviously this was the original algorithm. Later on they probably modified it, and now it's again a black art, as they said. So now we don't really know what is the algorithm using. Of course, now we know that it's personalized according to your previous search and many other things. But the basic mechanism is still based on PageRank. But before, a few years ago, you could really go to a web page and see what was when you were looking at the page, you had its PageRank score on the global network, which was provided. So many other centralities exist, but the problem is how to interpret them. So the one I presented here, I've chosen them because they are relatively simple to understand, and they are also available in most libraries and tools. So you can actually compute them on your graph. There are many other ones that exist, but they are harder to interpret, and often they are not implemented in many cases. So you will have to re-implement them to use them, and that's not the goal of this class. Just a final slides to explain you, so to show you really the difference in practice. So in general, when I'm doing this class live, I ask you to try to guess what is the centrality which is used in each of the graph. But here I will just explain you how to read it, basically. So if you look at this graph, so the more red is the node, or black, the most dark is the node, the highest the value. And here you can see that, for instance, in this graph, we are representing the degree, and we see that this node, which has a lot of neighbors, has a very high value. Also this one, because it has many neighbors. While this node has a lower value, even though it seems to be important because it's in the center. So in this case, it's really, you can recognize that it's the degree because the nodes with many neighbors have very high values. This one is a clustering coefficient. So actually you see that these nodes have a value of 0 because they are not part of triangles. So you cannot see it, but there are no links between these pairs of nodes. So these nodes are not part of any triangle, so the clustering coefficient is 0. Their friends are not friends between them. There is no friend of my friend are my friend phenomenon in this part of the graph. Only here you see that there is a triangle, and so these nodes have a clustering coefficient which is non-zero. These two are closeness and harmonic centrality. So if you remember, they are very similar, but you remember the closeness that has this notion of being really in the center of your graph. And here you see that in your graph, if you take kind of the middle, the center, you have the node with the highest closeness. And then the nodes which are very close to the center, they have high values. And if you go to the nodes which are really at the periphery, they have low values. Same for harmonic centrality. This one is the Betweenness, and so the Betweenness, you see that the node that stands to, so you see that if I remove this node, I will disconnect several parts of the graph. So this node is very important in terms of Betweenness because you need to go through this node to go from one part of the network to other parts. So logically, it has the highest value. But you see that, for instance, this node, which has a very low degree, it has only 2 neighbors, still it has a high Betweenness because it connects all these nodes to the rest of the graph. So high Betweenness. This one I have not introduced it. The Eigenvector Centrality is harder to recognize, but typically it tends to be what we could call rich get richer, a rich club, actually, rich club phenomenon, which means that these nodes, since they are important, they give their importance to their neighbors, and so it forms a group of important nodes in some dense area of the graph. And finally, the PageRank, which kind of solves this problem. And so the nodes that are the most important are nodes that well, kind of are, how to say, they are also connected to many nodes and are important. So it's harder to grasp what is this. But for instance, you can guess that these nodes, they are important because they are connected to many other nodes. That's kind of how to say, it's kind of a hierarchical organization, and all these nodes, they are connected to it. So this node is kind of the leader of a group of nodes. That's one way to interpret it. So so I give you this exercise. So if you want, you can pause the video and you try to solve with the 4, let's say, relatively simple cases, and you can try to guess which one is which one. So I let you pause the video if you want. Otherwise, I will switch to the answer in 3, 2, 1. Okay. So again, you can recognize the most simple, these simple centralities. This one, you clearly see in the center the importance. So it's the closeness. Okay. So this idea of being central, kind of a circle. This one is also simple because you see these nodes that are important for the flow, right? They are separating some part of the graph to other part of the graph. They are intermediaries, they are bridges. So these are betweenness. Here you have nodes with many connections in red, so they correspond to degree. And in this case, you see that you have this rich club, and this corresponds to the Eigenvector Centrality. Here, so some important part of the graph is discovered. So you see that different centralities capture different notion of importance, and so depending on what you're searching for, you might use one centrality or another one.